On Earth, the situation may boil over with many more devastating tragedies ensuing, and Earth's ultimate end might just have started happening. The big ones have missed us for the last 150 years, however, according to Neil deGrasse Tyson, we just might be out of luck. Unfortunately for us, the sun has just belched out an absolute beast of a flare. This could lead to a multi-trillion-dollar disaster. We've never been in more danger than now. What is this massive solar flare all about, and what impact would this horrifying flare have on us? Join us as we explore the biggest solar flare in 17 years that just happened. Our sun, like all active stars, is a burning ball of gas and plasma. At its nuclear fusion reactor core, the sun is burning at temperatures greater than 1,000,000 degrees. Therefore, the presence of aggressive encounters should not come as a shock. The sun does have its furious moments, and when they happen, it's awful news for Earth. Solar astronomy was an incredibly straightforward field from the early to mid-18th century. Just by staring at the sun's light, you may learn all about it. The light may be filtered using a prism to reveal its many wavelengths, beginning in the ultraviolet and continuing through the visible light spectrum's many hues, and finally into the infrared. Sunspots can be seen by looking directly at the solar disk through a solar filter or a projected image of the sun, both of which can be used with a telescope. Alternatively, you can witness the most aesthetically pleasing natural phenomenon, a total solar eclipse, and see the sun's corona. For more than 2 centuries, it was all, and everything changed when the Fire Nation attacked. No, we meant that everything changed when solar astronomer Richard Carrington began following a huge uneven spot in 1859. All of a sudden, a white light flare was observed with unprecedented brightness and lasting about 5 minutes. The biggest geomagnetic storm that Earth has ever seen happened around 18 hours later. Even those on the equator could see the aurora. Miners awoke in the middle of the night thinking it was dawn. Newspapers could be read by the light of the aurora. Worryingly, despite being completely disconnected, telegraph systems started sparking and setting flames. What we currently know as a solar flare, an example of space weather, was actually first observed at this time. A multi-trillion-dollar catastrophe would ensue if an event comparable to the Carrington event of 1859 were to happen on this planet today. The Earth's magnetic field has a tendency to direct charged solar particles that collide with it toward the planet's poles. While an aurora borealis is the usual outcome of solar particle interactions with Earth's upper atmosphere, the possibility of significant changes to the terrestrial magnetic field and the induction of currents is too great to ignore. The 2 main aspects of the sun that typically come to mind when discussing it are its nuclear fusion core, which is the primary source of its power, and the radiation it releases from its photosphere, which serves to both warm and power various biological and chemical processes both on Earth and in other parts of the solar system. There are other processes involving our sun, but these are 2 of the most important ones. The sun's topmost layers, in particular, reveal loops, tendrils, and even streams of ionized plasma atoms so hot that their electrons were stripped away, leaving only their nuclei. When examined closely, these ethereal characteristics are caused by the sun's magnetic field, which guides these heated charged particles as they move across the solar surface. Compared to the magnetic field of Earth, this is completely different. In contrast to the Earth's magnetic field, which emanates from deep within the globe, the sun's field is produced only below the surface. Due to the powerful magnetic fields that repeatedly loop back, separate, and reconnect, lines enter and leave the sun in a highly chaotic fashion. These magnetic reconnection events can cause charged particles to accelerate rapidly and cause changes in the strength and direction of the field near the sun. This has the potential to trigger solar flares and, in the case of the sun's corona, coronal mass ejections. Unfortunately, solar events don't necessarily remain localized there. They can and do travel freely around the solar system. Rapidly moving charged solar particles, mostly protons and other atomic nuclei, are what make up solar flares and coronal mass ejections. These particles are normally emitted by the sun in a continuous stream called the solar wind. Solar flares and coronal mass ejections are examples of space weather events that can increase the density, velocity, and energy of charged particles released from the Sun. When solar flares and coronal mass ejections do occur, they tend to happen in the Sun's mid and central latitudes rather than the pole regions. Their directionality appears to be completely arbitrary. Every direction toward Earth has an equal chance of occurrence. In our solar system, the majority of space weather occurrences are harmless, at least from Earth's perspective. It's only when an event comes directly for us that it poses a potential danger. Now that we have observatories and satellites that track the Sun, they serve as our initial line of defense, warning us of any possible danger from space weather. This happens when a flare is aimed squarely at us or when a coronal mass ejection looks annular or like a spherical halo around an event that might be headed our way. Unfortunately, a massive solar flare recently erupted from the Sun, causing a moderate radio blackout in South America and producing spectacular auroras for the last few days. Although this solar flare is the strongest seen in 6 years, scientists warn that it may only be the beginning of a series of events leading up to the solar maximum. As far as solar flares go, this one was the biggest since 2017. Solar flares will most likely become more frequent and, at their strongest, more destructive as we approach maximum solar output. An active sunspot region called AR 3514 was the culprit behind the flare. A solar flare of class X 2.8 was the official designation of the event. The number indicates the intensity within that category, and the letter X indicates that it is the most intense of the 5. The event was also categorized as R3. Solar flares, which can trigger radio blackouts, are measured on the R scale. The R scale ranges from R1, which is minor, to R5, which is extreme. There were more events besides the amazing flare. A solar flare is a powerful explosion of electromagnetic radiation that can swiftly traveling to Earth. Although coronal mass ejections are less powerful, they do discharge plasma and a magnetic field. It may take days for these coronal mass ejections to reach Earth. Thankfully, this flare only made a glancing strike toward Earth and not directly at the planet. This is crucial because direct impacts from flares and coronal mass ejections to Earth might amplify the problems already present. A solar flare or coronal mass ejection may release a shower of charged particles towards Earth, but it doesn't necessarily spell catastrophe. The only way things can go wrong for us is if these 3 things happen simultaneously. In order for space weather events to breach Earth's magnetosphere, they must be in the correct magnetic alignment relative to our home planet. Assuming the alignment is incorrect, the Earth's magnetic field will safely divert most particles, allowing the remaining ones to merely produce a fairly innocuous auroral display. Solar flares typically only affect the photosphere of the Sun, but when they contact with the solar corona, typically through a solar prominence, they can trigger a coronal mass ejection. The biggest threat to Earth would be a coronal mass ejection that was headed directly for the planet and had very fast particles. A substantial quantity of electrical infrastructure, including large area loops and coils of wire, must be established. Although it is now an integral aspect of our worldwide infrastructure, electricity was nonetheless unusual and novel in 1859. Space weather events pose a growing hazard to our infrastructure due to the increasing interconnection and reach of our electrical networks. That is to say, the vast majority of space weather events in Earth's history would have been harmless to people on Earth, as their only noticeable impact would have been to provide a breathtaking auroral show. But now, with the vast amounts of infrastructure dependent on power that increasingly envelop our world, the threat is really serious. The idea of induced current has been around since the middle of the 19th century, and it's not hard to grasp. Usually, when we construct an electrical circuit, we make sure to incorporate a voltage source. This might be a power outlet, a battery, or any other item that can generate electric charges and transmit them over a wire. That's the standard method. But another is to alter the magnetic field within a wire loop or coil. This produces an electric current. A change in the internal magnetic field can be achieved by applying an electric current to a wire loop or coil. The field reverses direction when the current is cut off. A fluctuating current generates a magnetic field. Actually, the inverse is also correct. Michael Faraday demonstrated this 190 years ago in 1831. Even in the absence of a battery or other voltage source, electric charge can be generated by manipulating the magnetic field within a wire loop or coil, for example, by inserting or removing a bar magnet. This process induces an electric current in the wire. It's not that space weather directly harms people, but it can generate massive electrical currents that may damage our infrastructure if it were to impact Earth. Among the many potential consequences that may manifest later on are electrical shorts, fires, explosions, power outages, blackouts, and the destruction of communication infrastructure. Most consumer electronics would be safe to leave unplugged in the event of a solar storm, so they aren't a big concern. Unpredictable surges will destroy power stations and substations and inject excessive current into towns and buildings. This is the main problem with the infrastructure designed for large-scale power production and transmission. A large one, on par with the Carrington event of 1859, would be a multi-trillion-dollar devastation that may kill thousands, if not millions, of people, depending on how long it took to bring heat and water to the areas hit the hardest. If we are truly committed to avoiding the worst-case situation, early detection should be our top priority for investment. We can see the sun from a distance and get a sense of when coronal mass ejections and flares might be dangerous to Earth, but up until now, our data has been lacking. We can only determine the severity of the possible catastrophic impact on Earth by monitoring the magnetic fields of charged particles flowing to Earth from the Sun and comparing them with the direction of Earth's magnetic field at that exact instant. Looking back further in time, we can see that there were a few solar storms that dwarfed the Carrington event. Old memories stay with trees in concentric annual rings. Each growth year records bits and pieces of the environment at that moment. By analyzing those rings, scientists are able to piece together events from Earth's history. In the year 775, a solar tsunami of atomic particles washed over Japan, as some cedar trees remember. Trees absorb radioactive carbon-14 from the air, and those trees showed a considerable increase in that variety of carbon. A new element called carbon-14 is created when cosmic rays, which are spaceborne extremely fast particles that bombard Earth on a regular basis, collide with nitrogen in the atmosphere. Carbon-14 production increases when the Earth is bombarded with an overabundance of cosmic rays, as happens with some solar flares. About 20 times bigger than the Sun's regular ebb and flow was the fluctuation in carbon-14 levels reported in 775. The clear suggestion there was that super events could happen because this was a factor of 10, if it was a solar flare, a factor of 10 or 20 or more greater than the Carrington event. Extrapolating further into the past, research into ice cores reveals a third comparable occurrence in 660 BCE. In addition to the 775 incident, scientists found two more spikes in carbon-14 levels in tree rings at approximately 7176 BCE and 5259 BCE, which may be equivalent. The Carrington event and these recent storms are difficult to compare side by side. There is no way to compare carbon-14 concentrations from the 1859 flare because it did not rain particles on Earth. On the other hand, the 775 occurrence seems to have been among the most powerful solar particle storms documented in the past 12,000 years. Our sun-observing satellites have been operating at L1 Lagrange for the past few years. The sad truth is that solar particles usually take around 15 to 45 minutes to reach L1 after having traveled 99% of the distance to Earth, to say nothing of taking action to lessen the impact of a geomagnetic storm. That is far from ideal. Everything is about to change, though, as the first of the next-generation solar observatories has recently come online. The National Science Foundation's KIST, or the Daniel K. Inouye Solar Telescope, its 5 scientific equipment include 4 spectropolarimeters, which are specifically engineered to measure the magnetic properties of the Sun specifically. It enables us to gauge the magnetic field in the solar corona, chromosphere, and photosphere, the three viewable regions of the Sun. With this data in hand, we can confidently ascertain the orientation of the magnetic field of a coronal mass ejection at the time of emission, easily ascertain the type of threat that ejected material presents to Earth. A warning of up to the full 3 to 4 days it usually takes for ejected coronal debris to travel to Earth might be issued. Instead of less than an hour's notice, we would still have around 17 hours of warning even for an event similar to Carrington, which travels at a rate 5 times faster than average coronal mass ejections. This is far more than what we had before. In its initial revelation in 2020, as the first of our next-generation solar observatories, the Inouye telescope measures the Sun's magnetic field and so provides us with the best warning system we've ever had for a possible geomagnetic disaster. The risks we face must not be overstated or minimized. Flares and, less frequently, coronal mass ejections are caused by magnetic events, but the Sun normally discharges charged particles. Typically, these streams of particles have low energies and move slowly, taking around 3 days to travel the distance between the Earth and the Sun. Since these cosmic occurrences tend to be somewhat localized, the chances of their impacting our planet are quite low, and the vast majority of them will pass right by. Our planet's magnetic field will divert them safely, even if they do collide with Earth, barring any chance of accidental anti-alignment between the forces. But if the stars align in the wrong way, which is really just a question of time and chance, the result might be catastrophic. While these particles won't be able to hurt living things on a direct level, they might wreak havoc on our infrastructure that relies on electricity and technology. The global electrical grid could collapse at any moment. The potential cost of repairs or replacements could exceed $2.6 trillion in the United States alone, depending on the severity of the damage. Another catastrophe could occur if low Earth orbit becomes too crowded, a cascade of collisions made inevitable if the systems responsible for collision avoidance are knocked offline. This could happen if space-based infrastructure, such as satellites, is disabled. An equally powerful solar flare as the Carrington incident of 1859 was released by the Sun on June 23, 2012. That had never happened before, not since we had the technology to track the Sun with such accuracy. The flare happened on Earth's orbital plane, but the particles were 9 days too far away for us to feel them. Particles made the journey from the Sun to Earth in a mere 17 hours, much like the Carrington event. If Earth had been in the way at the time, the global damage toll could have crested the $10 trillion mark, the first 14-figure natural disaster in history. It was only through luck that we averted catastrophe. We aren't much better off now than we were 9 years ago in terms of mitigating tactics. To avoid damaging houses, companies, and factories with huge induced currents, we need to improve the grounding of our stations and substations. Although it has never been done before, we may instruct power providers to gradually reduce the currents in their electrical networks over the course of 24 hours. This would reduce the chances and severity of fires. Even though there aren't any official suggestions at the moment, we could offer suggestions for how to handle things at home. The first step is early detection, and there have been tremendous scientific advancements in this area to better prepare for the next solar storm. It helps to have a better grasp of how powerful these storms may be. This, in turn, sheds light on what the cosmos may throw our way. The Carrington event was not a one-off, it was just a sample of what the Sun can do. If research into past solar flares has taught us anything, it's that humanity shouldn't be wondering if a similar solar storm could happen again. All we can wonder is when and hope for the best. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.